Hi Calculus 2 students. Today we're going to do trigonometric substitution. What we're going to do when we have something of this form is we are going to let x equal a sine theta so that we can get things in terms of angles instead of just plain x or y. And then we're going to see what happens as we do this. We'll be able to transform our integrals into something that we can integrate. For instance, we're going to verify that the area, that's not an A, we're going to verify that the area of this circle is pi a squared. So area equals. We're going to integrate this thing and find the area under the curve. Well, I just want to integrate a quarter of it because it makes things easier. It's symmetric all around. I'm going to integrate this from 0 to a and just the area under the curve, which would be a squared minus x squared dx. My trick on this is to let my x equal a sine theta. Well, that means I need to figure out what dx is. So dx in this case would then be a cosine theta d theta. Remember that a is a constant. So I've got 4 integral of a to 0 square root of a squared minus the quantity a sine theta quantity squared, and then I would get times a cosine theta d theta. Still plugging away at this. I'm going to get an a squared in each. I'll be able to factor that out and pull it. And then I'm going to have 1 minus sine squared, which is then just going to be a cosine squared. So let me write that down. Okay, I've got that written down. Now I've got the square root of cosine squared, so that's just going to be cosine theta. I'm going to multiply here and get cosine squared. Then I'm going to use one of my techniques from the previous section, which is to use those double angle formulas and half angle formulas, so I will get that for you. Of course, I had to go back and adjust my limits of integration. As soon as I went to plug them in, I went, oh, I didn't change from x to theta, and I need to do that, so I wrote that up here at the top. Changing from x to theta, I get pi over 2 and 0, and when you plug all of that in, then you will get 4 a squared, and you're going to get times pi over 4, and then you're going to get zeros after that, which is then going to get you pi a squared. For our next problem, I still have this a squared minus an x squared, so I'm once again going to let my x equal, and in this case our a is a 4, so 4 sine theta. That would lead to dx being equal to 4 cosine theta d theta. And we'll see where this leads us in our substitution. Alright, so I'm going to have integral of, and dx is then 4 cosine theta d theta. It's going to be over 16 minus, then I'm going to have a 16 sine squared theta, all to the 3/2 power. In which case, in this, I'm going to factor out that 16, then I'm going to have over cosine squared and see where I get from there. Alright, this is what I get using my results from last time. I pulled the 16, took the square root, which is 4, and then still had to cube it, and this 1 minus sine squared is then going to be cosine squared. Take the square root, that'll be a cosine, and then cube it, and this is going to give me the integral of, so I'm going to go ahead and write the 1 over 16 out front. One of those 4's cancel. Then I have just a plain old secant squared theta d theta, and this one is pretty. This is then 1 over 16 tangent theta plus c. Oh, but wait a minute. I don't really care about tangent theta. I need to get this back in terms of x's. So I'm going to have to draw my triangle for this. Okay, I have my triangle drawn from my original, which is this right here. And tangent theta happens to be, tangent is opposite over adjacent. So this would be x over square root 16 minus x squared plus c. And you could clean that up just a little bit, write it together, be a little nicer. I guess I should do it. And there you have it. Nice. Alright, or to evaluate the arc length of that segment, they have given us the equation for this, the integral. It looks pretty darn close to this one, but not exactly, so I need to have this as just a plain old x squared. So let's write that as, I'm going to divide this through by a 4, which means if I'm going to do this top and bottom just like I would a denominator, which essentially means that if it was a 4, when I take it out of here, it's a, well, I'll just do it slower. Okay, I've rigged it now. Multiply top and bottom here by 4 over 4. I get to pull this 4 out because I don't really need it, so he's just a constant multiplier 2. Run this 1/4 all the way through here. Now I have my x squared all by himself, and I can see that my a in this case is 1/2. And I'm going to do my trigonometric substitution. Oops, now my limit of integration won't be at 2. I don't want to make that mistake again, so I'm going to wait on that. So let's see, this is going to be, I'll put the 2 out front, and then I'm going to have square root of, and looks like I'm just going to write my same 1/2 quantity squared plus this 1/2 tangent theta quantity squared, because it is multiplied by my a, and my a is the 1/2. Alright, so I had to get that dx so that I could replace that, and that's going to be 1/2 secant squared theta d theta. I'm just leaving out my limits for right now. This 1/2 is going to go out front, so you're going to cancel there. This is going to end up as square root of, the 1/2 can actually be factored out, so it's going to be 1 over the square root of 2. That's going to be 1 plus tangent squared, which is then just secant squared theta times secant squared theta d theta. Square root of the secant squared is just a secant, so I'm going to get a secant cubed. I'll write that down. Alright, I had to change this to a, it is a 1/4, and when it comes out it is A2. Good grief. Alright, I think I have that now. And then now I'm going to rewrite, because I have fixed that little constant error. I went in and got my secant reduction formula, so this is the one I'm going to use with n equal to 3, and I'll write that down. Alright, this is what I have so far using that reduction formula. So now I'm going to go and get my theorem where I have the integral of secant theta involving those natural logs, so I'll go get that. Okay, I went and got it. So still moving along on this. I'm just going to write down this, and then I will go back and write this back in terms of x so I don't have to change my limits of integration. Okay, so I've done that. I went ahead and created my triangle so that I could go back. Tangent is opposite over adjacent, and then I just use Pythagorean to get that. So that means I've got 1/2, well, let's just write that as 1/4. Secant theta would be cosine. Cosine is adjacent over hypotenuse, so I just write the opposite of that. 1 over square root of 1 plus 4x squared, and then my tangent theta, which is of course 2x. I'm just going to go through and do this for the rest of them. But this time I'm going to write hypotenuse over adjacent like I said, 1 plus 4x squared over adjacent because it is secant, plus, and then carry on from there. Alright, I have all of those plugged in. My limits of integration, now I can just do that as a 2 to 0, and I'm going to plug all that in and see what I get. Alright, after that big old long messy thing, you can say that this is the exact answer, or you can say this is my approximate. Well, this one looks kind of sweet. It looks like this tangent one here. So let's go ahead and do x equals, my a in this case is 1, tangent theta, get my dx, and that would be secant squared theta d theta. I'm going to do my substitution and look at it for a second. Okay, not too bad because this is rigged to be secant squared, and then I'm going to square it, so I'm going to get the integral of, and it's going to be secant squared theta d theta over secant to the 4th theta, which of course that's going to end up being 1 over secant squared, which is just cosine squared theta d theta. Okay, well, I've done that one before. I'm just going to use those double angle formulas, and in substituting I'm going to end up getting theta over 2 plus sine 2 theta over 4 plus c. Now I need to make my little triangle for my back substitution. So this is my theta. Tangent theta is opposite over adjacent. Using the Pythagorean, I end up with 1 plus x squared here. Alright, pretty good so far. Alright, I went back and got one of my friends this double angle identity here. This is just going to be 1/2 the inverse. I'm going to take the inverse tangent on both sides, so that's just inverse tangent of x plus, and I'm just going to call it 1/4, and then 2 times. Now the sine of theta is opposite over hypotenuse, so I'll be writing x over square root of, I'll go ahead and write the rest of the, and simplifying that, this is what we get. So I'm going to move on to the next example. Now I could solve this one by using this guy right here and doing my trigonometric substitution, but I recognize this guy as something that we had done before, and he's this one right here where my a is 2, and well, you could practice once again doing it as we did before. I'm not going to. So this would be x over 2 plus c. All done with that one. I don't see anything here that looks like any of this. I do see, and I don't want to see it, but I do see an x plus 2 here, and I could complete the square and see what that leads me. At this point I don't see any other option but to try that. It might or it might not work. All you can do is just give it a whirl. So I'm going to complete this square and see what I get. Alright, I see some sort of, if I do a u substitution, I see I'm going to get some sort of u squared minus an a squared, so it's probably going to look like this one. I don't really want it to, but it is. So I'm going to go ahead and let u equal to x plus 2, and then du is going to equal dx, and I'll be able to use this thing right here, but it's going to be messy. Okay, I've done it. Now what I need to do is I'm going to let u equal this 3 secant theta. That means I'm going to need du, and du is going to be 3 secant theta tangent theta d theta. I'm going to substitute all that in. Okay, still rolling along here. I did my limits of integration too. So this is going to end up being a 3 on the outside because it's a 9 in there. Take it out, that's a 3 on the outside. That's going to be a tangent squared, which is just going to be a tangent theta. This 3 secant and this 3 secant go away. I'm just going to write tangent squared d theta because that's what it is. And then I can write that this is equal to the integral of, put a 3 out front, pi over 3, 0. That's just going to be secant squared theta minus 1 d theta. And that one is really pretty because that's just going to be tangent theta. This one's really pretty because it's just going to be theta, and I'll write that down. Alright, now I just need to evaluate that, and when you do, you end up with 3 square roots of 3 minus pi. Lovely. Alright, see you at the collaborate.